In this video, we will continue the discussion for the 3D kinetic study for the rigid body. For a rigid body that is performing rotation, so you have learned how to compute the angular velocity due to this rotation here at the center of mass, which can be computed by using this formula. If the velocity at the center of mass here is non-zero, then you have a translational velocity of this rigid body. So the rigid body is doing the angular motion and translation motion at the same time. To find the angular momentum of this rigid body with respect to an arbitrary point P here, we can use this formula. From the Newton's law, we have learned that the equation of motion of a particle can be written in this format, where the summation of force acting on the particle is equal to the change of the linear momentum with respect to time. Or it can be written in this format, where the mv is the linear momentum. By using the same analogy, Euler formed the equation of motion for the rotating rigid body, where the summation of torque acting on a rotating rigid body is equal to the change of the angular momentum with respect to time. So you have mv equal to the linear momentum. If you multiply with the radius, this is angular momentum. In simple, if we apply force on a body, then the body will experience change of the linear momentum. If we apply the torque to the body, then the angular momentum of the body will be changed with respect to time. This equation of motion can be further derived into the change of the angular momentum with respect to time that is observed or measured from the non-inertial frame plus the rotating effect. So when we expand this, we obtain the change of the angular momentum with respect to x, y, z component. And if you expand it and calculate the determinant, then you can obtain at the I direction, you need to cross this row and column, and then you need to take the determinant for this. So ohm y multiplied with hz, you obtain this component, minus with hy multiplied with ohm z, which is this. And if you repeat for the y and z direction, you should obtain this answer. You can further simplify the torque equation into this by attach the axis to the rigid body here at three principal axes. Let this to be the x, which is perpendicular to the plane of this thin disc. Let's say this is y and this is z. Previously, you have learned that if you attach the axis at the principal coordinate here, then the product of inertia, which is the I xy, I yz, as well as I xz, will be vanished. So you can simplify this into this equation by vanish all of these components. And also, if you attach the axis to the center of point here, basically the axis here is the same with the rotating frame, and therefore the omega will be equal to ohm in this case. So you can just change the ohm to the omega symbol. For example here, so the summation of torque in three axes x, y, z is equal to the change of the angular momentum, which is I multiplied with the change of angular velocity, which is the angular acceleration in x, y, z component, plus the rotating effect component here, where the hy is equal to I y omega y. Ohm z here can be just changed to omega z, since you attach the axis to be the same with the rotating frame axis. Therefore, you obtain negative Iy omega z component, which is equal to this. So if you repeat for the rest, then you should be able to obtain this solution. From this equation, we obtain the torque acting in the x direction equal to this component plus this component. By using the same approach, you obtain the torque acting in y direction to be equal to this, and the torque acting in z direction will be equal to this. These relations are known as the Euler equations, which are extremely useful in the study of rigid body motion. So you have learned that the summation of torque can be equal to this formula. Conservation of angular momentum means that if there is no external torque acting on the system, which is equal to 0, so in this case, there will be no change in terms of angular momentum. In this case, the angular momentum, which is the h, will be just remain constant and is called as the conservation of angular momentum. For example, in this case, in the initial condition, which is the state 1, you are riding a bicycle where the tire is rolling to move forward. So in this case, the tire of the bicycle is doing the general plane motion, which is rotating at the same time translating. Let the coordinate x, y, and z to be this direction. Then the angular motion for the tire will be in the z direction, where we can write the angular momentum is equal to the mass moment of inertia for the tire multiplied with the angular velocity in this direction with respect to z-axis. Therefore, from the front view, when you are riding the bicycle moving forward, the omega will be always acting in the left hand side. So from the top view here, you can see that the omega, due to the rotation for the tire in front here, which is tire A, and this is your tire at position B, so the direction will be in left hand side. So this is the z direction. With that, we obtain the angular momentum for the tire A and B at the first stage. Assume the tire to be hollow cylinder shape, where it's empty at the middle. So in this case, by referring to the appendix, the I in the z direction here will be equal to mr squared. Let's assume the mass is equal to 2 and then the radius is equal to 3. Substitute inside, we obtain the I. And let's assume the rotation speed for the tire is equal to 5 radians per second. With that, we success to obtain the angular momentum for the system, which is equal to 180. 18 multiplied with 5, we obtain 90. So this is the angular momentum from the first tire. Second tire has the same amplitude, therefore you obtain 180. For the total angular momentum for the whole system at the first condition. During the process, let's say there is no torque acting by the cyclist here. Since the summation of the torque is equal to 0, therefore your angular momentum will have no change, which is equal to constant. The length here represents the magnitude of angular momentum at the tire A and B. Since there is no torque acting on the tire, therefore the momentum will be just conserved and remain. So the length and the direction are just remain the same. This is what we mean by the conservation of angular momentum. If there is no external torque acting on the system at the first condition or first stage will be the same with the later stage. So the total angular momentum for a system at the first stage is equal to 180 and it will be just remain. One of the important applications for the conservation of angular momentum is to stabilize a rotating system. For example here, you see this guy wants to stable the bicycle, and this is hardly to be achieved when this bicycle is not moving. If the bicycle is rotated with constant angular velocity omega, then in this case, you have angular momentum I omega acting in left hand side of the bicycle when you are moving forward. Due to the conservation of angular momentum for the tire, so the h vector here will tend to remain in this direction at this magnitude if there is no external torque acting on the system. So in this case, the H will just always remain in the same direction and magnitude. This makes the tire of the bicycle stable when it is rotating. In this video, you can see a motorcyclist hit the motor when it is running in a very high speed, more than 100 km per hour. But why can't the motor fall when you hit it? So you can see the motor is actually stable itself. So why it can be so stable? From this example, we can see that if the rotation of the wheel spins faster, so in this case the rotating system will be more stable. This is known as the gyroscopic effect. This effect is direct result for the conservation of angular momentum. So due to this spin, you can foresee the angular momentum H here is equal to I omega. So if the omega is high, then the angular momentum will be high as well. With the absence of the external force or torque here, then the total angular momentum of the system must be retain the same strength and orientation. So you can see that the spin wheel here tends to stay in its original direction. When you hit the holder of the motor, let's say this is the holder. When you hit on the holder, you actually apply the torque to the system. So in this case, the torque is not equal to 0. So you can see that the holder will rotate in this direction due to the torque. So you can see the holder here is rotate counterclockwise to the vertical direction. Therefore, the torque is acting upward. The change of the angular momentum due to the torque is equal by this formula. So torque multiplied with the change of time is equal to the change of angular momentum. Let's draw the vector for the angular momentum for H1 here, which is the summation of the angular momentum at these two tires, which gives you a long vector here. The change of angular momentum due to the torque that we apply on this holder is drawn here. Since this is much more smaller compared to the H1 vector here, therefore the resultant of H1 plus the delta H here will approximate to H1. From here you can see the H2 is equal to H1. Since the angular momentum here remain constant and it doesn't affect by the small change of the angular momentum due to small torque here, therefore the H1 and the H2 after you apply the torque will still remain the same direction. So this is the nature of the spinning wheel, which tends to stay aligned in its original direction if the angular momentum is high. And this is the reason why a high-speed spinning wheel will provide more stabilization to the rotating system here. Imagine what will happen if a car hit the motor at this direction. When the motor was hit in this direction, you can imagine that you actually apply the torque in the vertical direction here in z-axis. So in this case, the torque caused by the car will be very high, which cause a high change in terms of angular momentum. So the delta H will be very high in this case, and it cannot be negated when you compare to the magnitude of H1 here. So in this case, the angular momentum is no longer conserved. The angular momentum of the wheel at the initial condition, stage 1, will change to angular momentum at second stage, due to the change of the angular momentum caused by the external torque given by the car here. So we can obtain the new H2 by taking the summation of H1 plus delta H. The resultant of H1 plus the delta H here will give you a new H2 in this direction. So this is where the wheel will spin. after it was hit by the car. Imagine that you are the observer looking at this accident and you stay at the view. So from your point of view, you see the wheel rotate initially in this direction, where your H is here. We use the symbol H1 to indicate the angular momentum of the wheel before the accident. During the accident, the car hit the motor and applied the torque in vertical direction. So this caused the change in terms of the angular momentum. This is what actually happened in the right hand side equation here. So how about H2 here? Since we know the H1 plus delta H will be in this direction, therefore the wheel will be spin to this direction. And this is your H2. So what you actually see here is that the wheel will rotate from vertical to this direction and it falls down. So you can see that initially the wheel is in vertical direction, where this is your H1. After we apply the torque delta H, then it will go to this direction where it falls down. In the previous example, we showed you that if we apply external torque to the system, so in this case, the summation torque will not be equal to 0, and the angular momentum will not be conserved, which means the angular momentum will be changed. By using the same example here, we have a bicycle with the angular momentum in the stage 1. What if the rider apply the torque to the system by lean to the left here? So in this case, the force is equal to mg, which is acting downward, and the radius is acting to the left hand side. Let's assign the x-axis is on the right, y-axis is moving upward, and z-axis is moving backward. If the force is acting downward with mg, and the displacement vector is moving to the left by r, we know that r cross the force will give us the torque, but where is the direction for the torque? So you can apply the right hand rule, take the r cross with the force here, then you should obtain the torque is acting in the z direction. So from the front view, you have the angular momentum acting in this direction. This is the top view, where your x direction is here, and this is your z direction, which is moving backward. Since you obtain the torque is acting in the z direction, therefore this is the direction for the torque in the z direction. The magnitude of the torque is equal to the mg multiplied with the radius, and this vector is equal to the change of the angular momentum, which is caused by the torque with respect to time. So we know that H2 is just equal to the summation of H1 plus delta H, and we draw the H1 and delta H in this direction. So where is the direction for H2? So from here you should be able to predict the resultant of these two vectors is equal to H2. Therefore the wheel will spin to this direction after we apply the torque. So this is the new H2. If we continue to remain at this position, we actually apply the torque continuously. So you can actually see the wheel is rotate in a circular pattern over the time. So this is known as precession. In this case, you have a spinning system rotate with omega. So the angular momentum of the wheel here is equal to mass moment of inertia multiplied with the omega. Let this direction to be x, the vertical direction to be y. So the z will be in this direction, which is the right hand side to this wheel. By using the right hand rule, you should know the direction for H1 is acting at the negative x direction, which is negative I. Initially, there is no mass in this system, so the wheel will just rotate in this direction. and the angular momentum is constant. When you add the mass to this system, you are actually introducing the torque to this system. Therefore, the angular momentum will not be constant and it will change over time. So you have the force equal to the mg from the mass, and you have the displacement vector measured from the center of the rotation to the mass. So we know that torque is equal to radius crossed with the force. Since the torque is no longer equal to 0 in this case, therefore there is change in terms of the angular momentum, and we say this is non-conservation of angular momentum. Can you predict where is the direction of the precession after you apply the torque constantly to this system? In simple, we want to know after you apply the torque by adding mass to this system, where is the new direction of the wheel to spin? Many of us might guess once we put the additional mass here, the thing will just pull down the wheel in the z direction. This is true when the wheel here is not spinning. Let's check if this is still true when the wheel is spinning. There is a correction for the x, y, z coordinate here. Based on the right hand rule, if this is x in front of the wheel, left hand side of the wheel should be y direction, vertical direction of the wheel should be z direction. First of all, we spin the wheel in the clockwise direction with respect to x-axis. So x-axis is in front of the wheel. This is the top view of the wheel, and this is the x-axis, which is in front of the wheel. And the wheel is rotated clockwise with respect to the x-axis. Therefore, your omega will be in negative I direction. The angular momentum of the wheel will be in the same direction here as well, which is equal to h1. And it can be computed by using the I omega. Let's have this direction to be your y direction and the vertical direction to be your z direction. So you put the mass on the spinning wheel and the wheel rotates in this direction with respect to z axis. When you add an additional mass in front of the wheel here, so the mass will create a force acting downward, and due to the radius with respect to the center of mass here, you are actually generate the torque, and this torque is acting in the counterclockwise with respect to the y-axis. Most of us think that the torque due to the mass here will cause the wheel to rotate in this direction, but this is not true when the wheel is spinning. So why does the wheel rotate in this direction, which is in the clockwise of the z-axis? To know this result, let's perform the analysis here. So you know that the angular momentum for the initial wheel is at this direction. Later you add the torque, which is in the y direction. So the torque will cause change in terms of angular momentum, where this is equal to the torque multiplied with the small duration of time. So you know that h2 is equal to h1 plus the change of the angular momentum. So take the summation of these two vectors, you obtain the resultant to be here. It means that the wheel here will rotate to this direction at second stage. Since the torque constantly acting on this wheel in the y direction of the wheel, so in the next stage, the resultant will be here, and the wheel will move to this direction, and it rotates clockwise with respect to the z-axis, and this rotation is called the precession. With that, you success to obtain the precession direction of the wheel after you apply the torque to the system. In this example, you see there is an heavy wheel where it cannot be held horizontally by this muscular guard. So it's so heavy. Why can this guy here hold it with one hand? Is it a magic, or we have anti-gravity view here? In fact, it's not an anti-gravity view, it still follows the Euler equation. So you have a heavy mass here acting downward, so the force is equal to mg, and this is the center where you hold the mass, and this is the radius. So the mass here is actually apply the torque with respect to this direction, and it's very hard to hold it by using one hand. But why can this guy here hold it with one hand? The secret is the wheel here is spinning with a high speed. The wheel is spinning in this direction, therefore you obtain the angular momentum of the wheel in this direction toward the guy. So you have learned that the existing angular momentum plus the change of the angular momentum due to the torque, which is the delta H, will be equal to the new angular momentum for the wheel. So when you take the resultant of the H1 plus the delta H here, you obtain the new resultant vector in this direction. Therefore, the wheel will spin to here instead of falling down. So you can see that this is the resultant. So you can see the wheel is just rotate in a circle instead of falling down. This is known as precession, or what we call the gyroscopic precession. And we can compute the precession frequency by using this formula, where the frequency is equal to the torque mgr divided by the angular momentum I omega. Gyroscopic effect and the steady precession is very important in our daily life. Imagine that the initial position for the helicopter here is in horizontal. The blade of the helicopter is rotated in a very high speed. Let's say this is the direction for the angular velocity. So how can we rotate the blade to this position? Many of the people might think we just need to apply the torque in this direction so that the blade will rotate in such a manner. However, this is not true. In the actual scenario, torque is actually applied counterclockwise to this direction to obtain the new position of the blade in this direction. From the top view here, we are actually apply the torque counterclockwise to this direction, where this is the upward force where you apply, and this is the downward force which give you this torque. Since the wheel is rotated in this direction, therefore you obtain the angular momentum in the vertical direction, and the torque is in this direction. Torque will give you the change of angular momentum, which is equal to torque multiplied with delta T. The resultant of the H1 plus delta H will give you H2, which is over here. By applying the torque in this direction, now we success to rotate the blade to a new position here. By understanding the gyroscopic effect as well as the steady precession effect, you learn how to properly apply the torque in order to control the position of the blade. Without the understanding of this, we can't design a proper mechanism to control the helicopter. In this example, you have a non-rotating wheel. When you move upward, you actually introduce a torque in this direction. So you can see that the wheel is just rotate in the same direction. You see a huge difference when you apply the torque on a rotating wheel. So when you move up, you apply the torque in this direction, but the wheel is rotate in this direction. So now you have learned the gyroscopic effect as well as the steady precession. And you should be able to explain why does the rotating wheel behave in such a weird manner. First of all, the rotating wheel is rotated in this direction, therefore you should obtain the omega here. And this is where you have the H1, which is the angular momentum. When you apply the force upward, and this is the center. You can obtain the radius here. Radius crossed with the force, you obtain the torque. By using the right hand rule, you should obtain the torque acting forward in this direction. Imagine you are this guy here and you see the motion of this wheel, and you should able to observe the H1 is moving downward and the torque is moving to the left. Torque multiplied with the delta T give you the change of angular momentum. So by taking the summation of H1 plus delta H, you obtain the H2, which is the resultant here. Therefore, the rotating wheel here will change from the H1 position to the H2 position here, due to the external torque. From this guy point of view, when you push the thing up, then this wheel will rotate in this direction. In 3D, it will be rotate in this way. Let's check the video again. When you push the wheel up, then the wheel will rotate in this direction. So this confirms our finding. The rotation motion of the 3D rigid body here is still follow the Euler law. In this case, you have a two-wheel vehicle that can be easily fall down due to the external force or torque. You can provide the stability to this system by having a spinning device here. If the spinning device is rotated with high angular velocity or high mass moment of inertia, then in this case, the angular momentum of this spinning will be high as well. The high-speed spinning device here will create the gyroscopic effect, which cause the spinning to be remain at this direction. As long as the torque acting on the system that cause the change of the angular momentum is small compared to the H here, then H1 will be just equal to H2, and the angular momentum can be conserved and will always remain at this position. This is how a two-wheel vehicle balances itself by using the gyroscopic effect. This technology can be very useful to provide a high stability to a system, as you can see in this video. This technology is very useful because it can help to balance the two-wheel vehicle from accident.